Okay, Taylor and Maclaurin series. Right now we are about to develop a technique which will allow us to write a power series representation for many more functions. So we begin by just considering the general power series representation where it's centered about A, and this is what it is. And so if we look at that, we might want to try to figure out what the coefficients might be. So if we work on that for a minute, we can think, well, what if we let x equal to a? So if we were to let x equal to a, all of these terms would go to 0, and so we would get f of a is simply equal to c sub 0. So that is the first coefficient. Now, what we can do is just, if you're playing around with this, one thing you can do is maybe start taking derivatives. So if we took a derivative, take f prime of x, what you get there is this goes to 0, and then we get c 1 plus 2 c2 times x minus a plus 3c3 times x minus a plus 4c4 times x minus a. And I'm sorry, this is x minus a to the first, this is x minus a to the second, to the third. If we do one more, plus 5, c5, x minus a to the fourth power, and so on. That's what we would get. All right. If we took the second derivative, this would go to 0, and we would get 2c2 plus 2 times 3 is 6, c3 times x minus a to the first plus 12 c4 x minus a to the second plus 20 c5 times x minus a to the third, and so on. If we took a third derivative, we could get f triple prime of x. This would go to 0, and we would end up with 6c sub 3 plus 24 c to the fourth x minus a to the first power plus 60 c sub 5 times x minus a to the second power plus some more terms. Let's do a couple more. F to the fourth of x. This would go to 0. We would have 24 c to the fourth plus 120 c to the fifth times x minus a to the first plus some more terms. F to the fifth of x, the fifth derivative of f, would give us, this would go to 0, we'd have 120 c to the fifth plus some more terms. Okay, so let's see what would happen if we let x be a. So if we say f of a, f prime of a, f double prime of a, f triple prime of a, f to the fourth of a, and so on, f to the fifth of a, what do we get here? Well, f prime of a, if we let all of these terms will go to 0 if x is a, and we'll just be left with c1. F double prime of a, all of these terms will go to 0, and we're just left with 2c2. F triple prime of x, at a, all of these terms would go to 0, and we just have 6 c sub 3. F to the fourth derivative of a, all of those would go to 0, and we just have 24 c sub 4. The fifth derivative of a, we'd end up with 120 c sub 5. Okay, so this is interesting. There is a pattern to these numbers. 1, 2, 6, 24, 120. What this ends up being, and if I wrote this differently, it'd be much easier to see. This 2 right here, for instance, is really 2 times 1. This 6 right here is really 3 times 2 times 1. This 12, how do we get that? We multiply 6 by 4, so 4 times 3 times 2 times 1. And so this 20 was multiplying this by 5. 5 times 4 times 3 times 2 times 1. So what we see is happening here is we are, these are factorials, in fact, that we're developing right here. So what we have here is, this is, something's bothering me here. No, this is okay. This is 2 factorial, C2. This is 3 factorial, C3. This is 4 factorial, C4. This is 5 factorial, C sub 5. And this is 1 factorial, C sub 1. And this is, you can consider this 0 factorial, C sub 0. 0 factorial, by definition, is 1. That's how that is handled. Okay, so I feel like I said something funny here, so let me check this out. No, that's not times 4. This would be a 2 at this point. Okay, so this is factorial. This 12 is not, because it hasn't been, the right thing hasn't been multiplied in yet. I messed up here. So just disregard that. This is true, though. 5 factorial is 120, 4 factorial is 24, 3 factorial is 6, and this is what this ends up being. So, if we were going to say in general the nth derivative of the function at a is equal to n factorial times c sub n. So if we wanted to solve for the coefficient c sub n would simply be the nth derivative at a divided by n factorial. That's what we could develop. This has been developed. And so we see that if the function f has a power series representation at a, that is, if we can write the function f of x as the sum from n is 0 to infinity of c sub n x minus a to the n, where it's got the radius of convergence, the absolute value of x minus a, then the coefficients are given by this formula. C sub n is equal to the nth derivative of f at a over n factorial. So that means we can write the expansion of a function as the sum of terms. F of x will be equal to f of a plus f prime of a over 1 factorial. This is the first coefficient times x minus a to the 1, plus the second derivative at a over 2 factorial times x minus a to the 2. This is c sub 2. C sub 3 would be considered this, and so on. This is called the Taylor series of the function f at a. Now there is a special case called the Maclaurin series, and the Maclaurin series is where we let a equal to 0. So in that case, f of x would equal to these coefficients, the nth derivative of f at 0 over n factorial x to the n. And so this is what the sum of terms would look like, f of 0, f prime of 0 over 1 factorial x to the 1. The second derivative of f at 0 over 2 factorial x to the 2 plus the third derivative of f at 0 over 3 factorial times x to the 3, and so on. This special representation is called the Maclaurin series of the function f. So we are about to see how we can write the Maclaurin series representation for the function e to the x. Okay, so e to the x is our function, so we've got the function f of x is e to the x. Now, this, if we're going to use the Maclaurin series, and they said that, then we're going to represent it's about 0, a is 0. So the representation of that is given by this function right here. So e to the x is going to equal to f of 0 plus f prime of 0 over 1 factorial plus f double prime of 0 over 2 factorial, this is, times x squared plus f triple prime of 0 over 3 factorial x to the third, and so on. So let's see what's going to happen here. Well, we definitely need to take some derivatives. So f prime of x is e to the x, and f double prime of x is e to the x, and f triple prime of x is e to the x. And the fourth derivative, the fifth derivative, and so on is still e to the x. Similarly, if we let this be about 0, f of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is 1. F double prime of 0, 1. F triple prime of 0, 1, and so on. So, we can represent this function as f of 0, 1, plus f prime of 0 over 1 factorial times x to the 1, plus f double prime of 0 over 2 factorial x squared, plus f triple prime at 0 over 3 factorial x cubed, plus f to the fourth of 0, not f to the fourth derivative of f at 0 over 4 factorial x to the fourth, and so on. This is what the e to the x series representation looks like. Can we write it as a formula? Let's see what that would look like. We could say e to the x is equal to, okay, we've got x to a power over that power to the factorial, and it starts at 1. So let's let our sum start at 0. E to the x, let me make this get the right place. E to the x can be represented as n is 0 to infinity. Let me check this out. When n is 0, we have x to the n over 0 factorial, which is 1 over 1. There's our 1. When n is 1, we have x to the first power over 1 factorial, okay? When n is 2, x squared over 2 factorial. Yes, this is the the Maclaurin series representation for e to the x. And so in a separate video, I'm going to show you graphically exactly what this means. But let's go ahead and figure out the radius of convergence, okay? A good way to figure that out is by using the root test. So let's take the limit as n goes to infinity of the absolute value of a sub n plus 1. So that's going to be x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. All right, that's going to equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. All right, so what can we do about this? This x to the n plus 1 is really x to the n times x. So this can be canceled out, and I just get an x right there. N plus 1 factorial is n plus 1 times n factorial. So I can divide that out, and I'm left with the n plus 1 in the denominator. All right, this limit is with n's, not x's. So I can rewrite this as, this is equal to the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. Well, this 1 over n plus 1, this is headed to 0. So the limit's going to be the absolute value of x times 0, which is 0. This will be less than 1 for all x values. This tells us that our radius of convergence is infinity. The interval would be negative infinity to infinity for e to the x. Okay, and in just a second, I'm going to show you graphically what that really means. All right, let's look at another example. Example 2, determine the Maclaurin series for sine of x. Find the associated radius of convergence. Okay, so for sine x, it's a Maclaurin series, okay? That means it's centered at 0. So we are going to be taking some derivatives. So our function f of x is the sine of x, right? So the first derivative, the second derivative, the third derivative, the fourth derivative, I just put a 4 right there, and so on. Okay, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of sine is cosine times that constant in front, -1, is negative cosine. And then the derivative of cosine is negative sine, so a negative times a negative turns this back to sine. And so we are starting to repeat our pattern here. So that means f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f fourth derivative at 0. We could go on if we wanted to. The sine of 0 is 0. The cosine of 0 is 1. The sine of 0 is 0 times -1 is a 0. The cosine of 0 is 1 times the -1 is a -1. The sine of 0 is 0. So this is going to be the pattern, the repeating pattern for our coefficients for our series. Okay, so now our series, it's the Maclaurin series, says f of x, so in this case the sine x, is equal to f of 0, which is 0, plus f prime of 0, which is 1, over 1 factorial x to the 1, plus f double prime of 0, which is 0, over 2 factorial times x to the 2, plus f3, the third derivative, at 0, -1 over 3 factorial x to the third, 0 over 4 factorial x to the fourth, and then it starts to repeat. So then it's going to be 1 over 5 x to the fifth, 0 over 6 x to the sixth, minus 1 over 7 factorial x to the 7. And so on. Okay, so let's just see what's happening here. Let me write this without the 0 terms. So the sine of x is really 1x, okay, plus 0 minus x cubed over 3 factorial plus 0 plus x5 over 5 factorial plus 0 minus x to the 7 over 7 factorial. And if I want to write this over 1 factorial, I certainly can. So let's see if we can write this formulaically. This is equal to the sum, as n is 0 to infinity of, let's see, we've got, these are odd powers, right? So how can we write our sine function? Let me think. It's going to be x to power of 1 and then 3 and then 5. So it's going to involve a 2n. X to the 2n plus 1 over that power to the factorial. Let's see if this is working. Oh, but I also have this positive negativeness going on, so I've got an alternating sign. I need to put a -1 to a power in here. So let me fix that. All right. N is 0 to infinity, -1 to the n. Let's see what happens here. If n is 0, this is positive. If n is 0, this is x to the 1 over 1 factorial. We just get an x. That's that term. Okay. If n is 1, we have our negative. Okay, our negative. 2n plus 1 is x cubed. 2n plus 1 is 3 factorial. This is working. This is working. So this is the Maclaurin series representation for the function sine x. Now, I'm also going to show you a little video of how these functions look graphically, how this works. Okay, but before I do that, let's go ahead and find the associated radius of convergence. Okay, so the root test is a good one for that. The limit as n goes to infinity. A sub n was n plus 1. Is that what I want to do here? Yes, it is. The absolute value of -1 to the n plus 1 times x to the 2n plus 1 over 2 to the n plus 1, the whole thing, factorial, divided by negative 1 to the n, x to the 2n plus 1, all over 2n plus 1, factorial. All right. The absolute values will take care of these guys. So that's good. So this is really equal to the limit as n goes to infinity of x to the 2n plus 2 plus 1 to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. All right. Okay, so what do we got here? This is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So if I divide that out, I'm just left with 2n plus 3 times 2n plus 2. Right here, 2n plus 1 would be left with an x squared is what I'm left with if I divide that out. So basically, I'm going to write on the back of this guy for room, we are to here. The limit as n goes to infinity of a sub n plus 1 over a sub n is being simplified down to x squared over 2n plus 3 times 2n plus 2. What I've done here is I've dropped the absolute values because x squared is positive and n is positive numbers. As n goes to infinity, the denominator totally overwhelms the numerator, and this limit is 0, which is less than 1 for all x. So the radius of convergent for sine of x power series is infinity, and the interval is negative infinity to infinity. Okay. Now, let's see. Now that we are armed with that, let's have a look at example 3. So it says, determine the Maclaurin series for the cosine of x, find the associated radius of convergence. We can absolutely go through what we just went through, finding all the derivatives and writing out the series with the coefficients and x to a power and developing a formula. And that is a fine thing to do. It works. But another thing we could do is notice that the derivative of sine, of x is equal to the cosine of x. So we could also say, hey, well, what is the sine of x? Well, the representation of sine of x is, here it is, that we just got through doing it. Let's take the derivative of this guy. The sum from n is 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. All right. Well, if we're going to take this derivative, what's going to happen? Negative 1 to the n is a constant, so he just gets multiplied on. Leave him alone. This would just simply be the sum from n is 0 to infinity of negative 1 to the n. This is a power rule. So the 2n plus 1 gets put in front times 2n plus 1. X gets raised to the 2n plus 1 minus 1, or just to the 2n, all over what we already had, 2n plus 1. That just gets carried through. All right, so let me just see if I like this. Throw the power in front and then raise it to 1 less. Yep, I like that. Okay, can we simplify this? We can. The fact 2n plus 1 factorial is 2n plus 1 times 2n factorial. So I can make this cancellation, and this just becomes 2n factorial. So this becomes n is 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. And this is the series representation for the cosine of x. Its radius of convergence is the same as sine. It's going to be infinity. All right, I'm going to take a pause here.